Okay, so what have I got here? What have I got here? I've got a bunch of LEDs configured to, and it looks like it's counting time. So this is leading straight into, I want to be looking at how we can get an accurate 1 second count. Because if we want to do something like measure time, then we want to be able to get an accurate count. So you can see that this is counting. If you have a look at the patterns, you'll get used to the pattern fairly quickly if you look at it. So there's 7, 8, 9, and then we tick over to 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41. And this is what's called binary coded decimal. So we have 4 bits which are for doing the tens of units, and 4 bits which are doing the units themselves. Now, of course, we don't have numbers greater than 5 in a clock, and so you can just see then that it went to 59 and then ticked over to 20 here, or 2 minutes here, sorry. So 2 minutes and 11, 12, 13, 14, 15 seconds. So that's us. We want this accurate 1 second time, and we can do this with our microcontroller. We just need to know how to do it. And so I'm going to share the screen now, and we're going to look at the next exercise. So let me just adjust my camera. Rightio. Here we go, back again. So what we've got here is an exact 1 second timer. And the way we do that is we have a, I'll just get my pointer, sorry. Annotation, little spotlight. So the way we do that is we start our counting from 0, but before it gets to the maximum, excuse me, before it gets to the maximum value, we reset the count at some other value. So what we're doing is we've got the output of our counter and we're comparing it with some predetermined value. And so what I've done is I've got a value in the simulator, which I'm going to show you. Let's see where this is, not there. Bear with me for a moment while I just find this, please. I had it queued up and then I let it disappear on me. Assignment presenter, here we go. So in the assignment, what you can do is go to the blank circuit simulator. Oops, there we go. And I've got some done code here for this sort of overflow thing. So let's import that. Okay, so what we've got here now is we've got exactly what we had in the previous simulation. We've got a clock, which is in this case not going through the prescaler. It's directly 16 megs going into the 16-bit timer. And what we're doing is this is counting up. But of course, when it gets to this value here in the comparator, it resets itself through this link here. And so what you're seeing down here is some timing between these output pulses and the interrupts. So we can actually make these quite accurate now. And so this is how it's done. And if we go to the data sheet, for instance, the data sheet for the Atmel microcontroller, I'll just pop that up here. Again, you've got to be really familiar with this data sheet, so get used to having a look at it. So we're going to look at the overview of the microcontroller. And here's what we've got. We've got our, again, our timer counter, which is 16 bits. It's counting up. It's counting up at this clock rate here. And the clock rate is coming in from this clock, which is from our prescaler or from our external pin on the microcontroller. And so it's counting up, but when it gets to a compared value here, so this is another register, output compare register 1A, when the count is equivalent to this, it sends a signal to say that, hey, we are now going to have need of something from our control logic. So there's the output there coming in to this. Now, at that stage, it will clear the counter, and then of course it will just tick back over and keep counting again. So we get this lower value of count. So what we're looking at is this output compare register. This is where we're going to put the value. So I put that here. The value is set up in output compare register 1A, time 1 being for timer 1. You will have noticed if you were looking that there was a counter B, a compare register B as well. Now, of course, what that means is we're going to have to change our code a bit. I just want to delete this. This is something that I was playing with, which was wrong. Here we go. Now, what we want to do is have a look at what we're going to change. We're no longer counting to the overflow point. So this interrupt that we had previously, the overflow vector, we need to replace with the compare A vector. Okay, so how do you find all of these? Well, they're actually listed in the data sheet. They're in the in this header file here, and of course in Atmel Studio, if you just start typing it, you'll find all the ones that are there. So when this gets to this compare A vector, it's going to just toggle the LED. So of course nothing's happening in our main loop. It's just every second, and pretty close to a second, we're going to get an interrupt, and it's going to toggle our LED. So how do we go about setting this up? Well, previously we didn't look at the waveform generation because the timer counter was in normal mode, which means that we're not looking at any of the special features of it. So now we are looking at a CTC, and we'll just go back to the timer counter register A, 1A, to have a look and see, here's our waveform generation bits. There's bit 1 and bit 0. And actually, we've got another 2, which are here, bit 3 and bit 2 are in this register. So you just have to be really careful about setting these bits as to which register you're writing which bits into, okay? So what we're going to do is, basically, those are all zeros for the normal mode, and we're looking for a table which will tell us what those are. And here it is here, our waveform generation mode bit description. And you will see that there are 0 through to 15 different options. And what we're looking for is for the counter to be cleared on a match. And this is the CTC mode, clear timer on compare match CTC mode. And so CTC mode requires us to set WGN1 bit 2, okay? So that's waveform generation mode for timer 1 bit 2. We're not going to worry about 3, 1, and 0. We're just going to set bit 2 to 1. Okay, so let's have a look at the code and make sure that we're in the right register. WGM12 is in, must be in timer counter compare register 1B. So yes, that's the bit we're going to set here, WGM12. So let's go to the code here. There we go, timer counter compare register 1B, and we're setting that bit, which is CTC mode. Great, so now we know that the timer will be reset when it gets to that value. It's actually not doing anything yet. We're just saying, hey, that's the value that we're going to reset you at. But we actually need to do some counting first as well, and that's what's done here by setting the clock source bits. That's how you activate the timing. Of course, this hasn't changed from the previous code. Okay, and what I'm doing now is I'm actually saying, well, I want you to do this reset of the counter on the clock after 62499. So this is again thinking about the fact that the counter will go up to 62499 and the reset will happen on the next clock cycle. Okay, so there we go. So this is the value we want to put into output compare register 1A. So output compare register 1A, just going back to our data sheet, overview, and we're looking at, here's output compare register 1A. So when the value in the timer equals this value, we'll get our reset through the control logic, and it will clear our clock for us. Clear our timer for us. Now, of course, we want this interrupt to occur. Now, the previous interrupt we used was the overflow interrupt. Well, an overflow interrupt will never happen because it's always been reset at output compare register 1A value. So we need to find out this new bit that we're going to use, and we're going to look on the timer mask for register for timer 1. So I'm just going to go back to the data sheet again, looking at my data sheet. I'm going to go to TIMSC 1, and I'm looking for the one that's to do with output compare match A interrupt enable. So that's it there. So I want to set this when this bit is written to 1 and the I or interrupt flag in the status register is set, in other words, interrupts globally enabled, the timer counter 1 output compare A match interrupt is enabled. The corresponding interrupt vector, see these interrupts, is executed, okay? So what we have to do is we have to set this bit here, output compare interrupt enable timer 1 A, and so that's what we're doing here, okay? And of course, then we also need to enable our global interrupts. And that's a very simple way of setting up a very accurate timer. So how did the timing work in this situation? So we're counting from 0 up to some value and then overflowing. So let's just have a little think about how we might work out a model for this. See what sort of model would we use to do this. Let's just think about first principles. What we're doing is we are counting. I'm just going to stop the share screen and we're going to go at a piece of paper here and see if we can get something going. So I'll just put this down here. One of the things that's upside down, of course, and that's this to do with this camera I've got. So I'm just going to do a quick change of this in Zoom. Where's my mouse gone? I'm going to change my video settings. I'm going to rotate. There we go. Now that's what I've got. Okay. So now I am hopefully sharing this screen with you. I'm going to turn some light on and I'm going to do the focus. There we go. So what we're looking at is we've got a counter which is counting from 0 up to some value. The value that is in output compare register 1A. If it kept going, it would get to 65,535 and overflow, but it doesn't. It overflows back to 0 and then keeps counting again to output compare register 1A. So how might we do this calculation? Well, what we know is that we have a 16 megahertz crystal. Right, here's our crystal, right, and that is going into our prescaler, and our prescaler is set at a value of divide by 256, and then it is going into our 16-bit timer. Okay, timer counter 1, and then of course we've got our comparator, which is comparing it to some other value in the output compare register 1A. So what value goes in here to give us an interrupt at 1 second? At 1 second counts. So let's just have a little think about this. So we've got 16 divided by 256. Well, we know some of these values already. So I'll go back through the document there in front of us. So 16 megahertz divided by 256 is 62.5 kilohertz, okay, which is a clock pulse of 16 microseconds. So what I'm going to do is I'm going to find a number that divided by 16, or 1 second divided by 16 microseconds will give me some value. So let's just have a look at that. And that value, of course, is, I'll just do this on my calculator. You can do it on your own calculator. So I'm dividing 1 by 16 microseconds, and I'm getting the number 62,500. But of course, I don't want 62,500 because it overflows then in 62,501. So really what I want is 62,499. So when this count gets to 62,499 on the next clock pulse, it will overflow and give me my interrupt. So we need a model for this. So I'm going to go back to screen share and I'm going to have a look at what's going on in the data sheet, for instance. We might be able to find something in the data sheet that is going to help us with this. So I think I'm back on screen share again. That's good. And what I want to do is start having a look in the data sheet for some values that might help me calculate the timer. So if I scroll through the data sheet, I'm actually in the register, but I want to go back up to the top, but the overview, start at the overview and go down, start looking to see if I can find a formula. Okay, because being a good student, I just look for a formula. to bang in some numbers. It's a pretty mean thing to say, isn't it? So what I'm looking for is formula. Gosh, I'm not going to find any formula in here. Surely there's got to be a formula somewhere in here which is going to help me set up my timer. So oh, there's some stuff here about output compare unit block diagram. Okay. Yeah, we keep going. Compare match output unit. This is what we're talking about. Modes of operations, normal mode, CTC mode. Oh, here's a diagram actually. Oh, and look what I found. I found the waveform frequency is defined by the following equation. Okay, so the frequency is clock over 2 times n, where n is it must be the variable that represents a prescaler. There we go, it's right in front of me. So I've got that, I've got my output compare value, I've got my 1 plus. So this you would think helps you understand what's going on, but it doesn't, okay? This here will give you a frequency of the pulse, which is perhaps coming out of our toggle pin at the moment. So this is exactly what we're getting. There is the frequency which is coming out of our toggle pin. And you can see that as we change the output compare value, the counter will count up to a lower value, so therefore the pulse will be shorter. And there we go, there's a number of short pulses. So here we can make a really nice, interesting pulse train of really specific things if we want to, or set it to a specific frequency. Now, looking at what I calculated in my model here of what's going on, and what's going on here is different. I want to draw your attention to the fact that just, you know, looking for a formula and dropping some numbers into it sometimes works and sometimes does not. So I want to think about the fact that the model I did was the period of a single interrupt. So that's one of these periods here, this one, or this one, or this one. And this formula is for calculating the toggle frequency. So both, it's got 2 periods. So that's why there's this extra factor of 2 in here. And of course, we're looking at frequency rather than period. So you know, if I ask you to work out the period or create a timer with a certain period, then just dropping numbers into this formula won't help you. You really need, again, just to understand what's going on here, doing the counting from 0 up to the output compare register number, or output compare register value, and then resetting will give you a single period. But of course, if we're toggling the pin to get a frequency out, we have to have 2 periods of time to get a full clock period coming out. So you just reiterated that again. We're calculating 1 period in time when this period here is referring to both the full toggle. Okay, so I am now getting a toggle which is on for 1 second and off for 1 second. Okay, so it's you know, it's half a hertz, right? It's got a period of 2 seconds. It's half a hertz. So it's I'm calculating this as 1 second and this is 1 second, and the full period is 2 seconds, and therefore the frequency coming out is half a hertz, which is where we're getting this divide by 2 here in this. So just be really aware of what you're doing when you're thinking about this, okay? Cool. So this will give us our exact 1 second. Now, I think that's enough for this. We'll just call it quits there. Cheers. Come back to it shortly.